Mental chronometry is the use of response time in perceptual motor tasks to infer the content, duration, and temporal sequencing of cognitive operations. Mental chronometry is one of the core paradigms of experimental and cognitive psychology, and has found application in various disciplines including cognitive psychophysiology, cognitive neuroscience, and behavioral neuroscience to elucidate mechanisms underlying cognitive processing. Mental chronometry is studied using the measurements of reaction time. Reaction time is the elapsed time between the presentation of a sensory stimulus and the subsequent behavioral response. In psychometric psychology, it is considered to be an index of speed of processing. That is, it indicates how fast the thinker can execute the mental operations needed by the task at hand. In turn, speed of processing is considered an index of processing efficiency. The behavioral response is typically a button press but can also be an eye movement, a vocal response, or some other observable behavior. Types. Response time is the sum reaction time plus movement time. Usually the focus in research is on reaction time. There are four basic means of measuring it. Simple reaction time is the motion required for an observer to respond to the presence of a stimulus. For example, a subject might be asked to press a button as soon as a light or sound appears. Mean RT for college-age individuals is about 160 milliseconds to detect an auditory stimulus, and approximately 190 milliseconds to detect visual stimulus. The mean reaction times for sprinters at the Beijing Olympics were 166 milliseconds for males and 189 milliseconds for females. But in 1 out of 1,000 starts they can achieve 109 milliseconds and 121 milliseconds, respectively. Interestingly, this study also concluded that longer female reaction times can be an artifact of the measurement method used, suggesting that the starting block sensor system might overlook a female false start due to insufficient pressure on the pads. The authors suggested compensating for this threshold would improve false start detection accuracy with female runners. Recognition or no-go reaction time tasks require that the subject press a button when one stimulus type appears and withhold a response when another stimulus type appears. For example, the subject may have to press the button when a green light appears and not respond when a blue light appears. Choice reaction time tasks require distinct responses for each possible class of stimulus. For example, the subject might be asked to press one button if a red light appears and a different button if a yellow light appears. The Jensen box is an example of an instrument designed to measure choice reaction time. Discrimination reaction time involves comparing pairs of simultaneously presented visual displays and then pressing one of two buttons according to which display appears brighter, longer, heavier, or greater in magnitude on some dimension of interest. Due to momentary attentional lapses, there is a considerable amount of variability in an individual's response time, which does not tend to follow a normal distribution. To control for this, researchers typically require a subject to perform multiple trials, from which a measure of the typical response time can be calculated. Taking the mean of the raw response time is rarely an effective method of characterizing the typical response time, and alternative approaches are often more appropriate. The evolution of mental chronometry methodology. Galton and differential psychology. Sir Francis Galton is typically credited as the founder of differential psychology, which seeks to determine and explain the mental differences between individuals. He was the first to use rigorous reaction time tests with the express intention of determining averages and ranges of individual differences in mental and behavioral traits in humans. Galton hypothesized that differences in intelligence would be reflected in variation of sensory discrimination and speed of response to stimuli, and he built various machines to test different measures of this, including reaction time to visual and auditory stimuli. His tests involved a selection of over 10,000 men, women and children from the London public, Donder's experiment. The first scientist to measure reaction time in the laboratory was Franciscus Donders. Donders found that simple reaction time is shorter than recognition reaction time, and that choice reaction time is longer than both. Donders also devised a subtraction method to analyze the time it took for mental operations to take place. By subtracting simple reaction time from choice reaction time, for example, it is possible to calculate how much time is needed to make the connection. This method provides a way to investigate the cognitive processes underlying simple perceptual-motor tasks, and formed the basis of subsequent developments. Although Donder's work paved the way for future research in mental chronometry tests, it was not without its drawbacks. His insertion method, often referred to as pure insertion, was based on the assumption that inserting a particular complicating requirement into an RT paradigm would not affect the other components of the test. This assumption, that the incremental effect on RT was strictly additive, was not able to hold up to later experimental tests, which showed that the insertions were able to interact with other portions of the RT paradigm. Despite this, Donder's theories are still of interest and his ideas are still used in certain areas of psychology, which now have the statistical tools to use them more accurately. Hick's law. W. E. Hick devised a court experiment which presented a series of 9 tests in which there are n equally possible choices. The experiment measured the subject's reaction time based on number of possible choices during any given trial. Hick showed that the individual's reaction time increased by a constant amount as a function of available choices, or the uncertainty involved in which reaction stimulus would appear next. Uncertainty is measured in bits, which are defined as the quantity of information that reduces uncertainty by half in information theory. In Hick's experiment, the reaction time is found to be a function of the binary logarithm of the number of available choices. This phenomenon is called Hick's law, and is said to be a measure of the rate of gain of information. The law is usually expressed by the formula, where n are constants representing the intercept and slope of the function, and is the number of alternatives. The Jensen box is a more recent application of Hick's law. Hick's law has interesting modern applications in marketing, where restaurant menus and web interfaces take advantage of its principles in striving to achieve speed and ease of use for the consumer. Sternberg's memory scanning task. Saul Sternberg devised an experiment wherein subjects were told to remember a set of unique digits in short-term memory. Subjects were then given a probe stimulus in the form of a digit from 0 to 9. The subject then answered as quickly as possible whether the probe was in the previous set of digits or not. The size of the initial set of digits determined the reaction time of the subject. The idea is that as the size of the set of digits increases, the number of processes that need to be completed before a decision can be made increases as well. So if the subject has 4 items in short-term memory, then after encoding the information from the probe stimulus, the subject needs to compare the probe to each of the 4 items in memory and then make a decision. If there were only 2 items in the initial set of digits, then only 2 processes would be needed. The data from this study found that for each additional item added to the set of digits, about 38 milliseconds were added to the response time of the subject. This supported the idea that a subject did a serial exhaustive search through memory rather than a serial self-terminating search. Sternberg developed a much improved method for dividing reaction time into successive or serial stages, called the additive factor method. Shepard and Metzler's mental rotation task. Shepard and Metzler presented a pair of 3-dimensional shapes that were identical or mirror image versions of one another. Reaction time to determine whether they were identical or not was a linear function of the angular difference between their orientation, whether in the picture plane or in depth. They concluded that the observers performed a constant rate mental rotation to align the two objects so they could be compared. Cooper and Shepard presented a letter or digit that was either normal or mirror reversed, and presented either upright or at angles of rotation in units of 60 degrees. The subject had to identify whether the stimulus was normal or mirror reversed. Response time increased roughly linearly as the orientation of the letter deviated from upright to inverted, and then decreases again until it reaches 360 degrees. The authors concluded that the subjects mentally rotate the image the shortest distance to upright, and then judge whether it is normal or mirror reversed. Sentence picture verification. Mental chronometry has been used in identifying some of the processes associated with understanding a sentence. This type of research typically revolves around the differences in processing four types of sentences: true affirmative, false negative, and true negative. A picture can be presented with an associated sentence that falls into one of these four categories. The subject then decides if the sentence matches the picture or does not. The type of sentence determines how many processes need to be performed before a decision can be made. According to the data from Clark and Chase and Justin Carpenter, the TAR sentences are the simplest and take the least time, than FA, FN, and TN sentences. Mental chronometry and models of memory. Hierarchical network models of memory were largely discarded due to some findings related to mental chronometry. The TLC model proposed by Collins and Quillian had a hierarchical structure indicating that recall speed in memory should be based on the number of levels in memory traversed in order to find the necessary information, but the experimental results did not agree. For example, a subject will reliably answer that a robin is a bird more quickly than he will answer that an ostrich is a bird, despite these questions accessing the same two levels in memory. This led to the development of spreading activation models of memory, wherein links in memory are not organized hierarchically but by importance instead. Posner's letter matching studies. Posner used a series of letter matching studies to measure the mental processing time of several tasks associated with recognition of a pair of letters. The simplest task was the physical match task, in which subjects were shown a pair of letters and had to identify whether the two letters were physically identical or not. The next task was the name match task, where subjects had to identify whether two letters had the same name. The task involving the most cognitive processes was the rule match task, in which subjects had to determine whether the two letters presented both were vowels or not vowels. The physical match task was the most simple. Subjects had to encode the letters, compare them to each other, and make a decision. When doing the name match task, subjects were forced to add a cognitive step before making a decision. They had to search memory for the names of the letters, and then compare those before deciding. In the rule-based task, they had to also categorize the letters as either vowels or consonants before making their choice. The time taken to perform the rule match task was longer than the name match task, which was longer than the physical match task. Using the subtraction method, experimenters were able to determine the approximate amount of time that it took for subjects to perform each of the cognitive processes associated with each of these tasks. Mental chronometry and cognitive development. There is extensive recent research using mental chronometry for the study of cognitive development. Specifically, various measures of speed of processing were used to examine changes in the speed of information processing as a function of age. Kale showed that speed of processing increases exponentially from early childhood to early adulthood. Studies of reaction times in young children of various ages are consistent with common observations of children engaged in activities not typically associated with chronometry. This includes speed of counting, reaching for things, repeating words, and other developing vocal and motor skills that develop quickly in growing children. Once reaching early maturity, there is then a long period of stability until speed of processing begins declining from middle age to senility. In fact, cognitive slowing is considered a good index of broader changes in the functioning of the brain and intelligence. Demetriou and colleagues, using various methods of measuring speed of processing, showed that it is closely associated with changes in working memory and thought. These relations are extensively discussed in the Neo-Piaget theories of cognitive development. During senescence, RT deteriorates, and this deterioration is systematically associated with changes in many other cognitive processes, such as executive functions, working memory, and inferential processes. In the theory of Andreas Demetriou, one of the Neo-Piaget theories of cognitive development, change in speed of processing with age, as indicated by decreasing reaction time, is one of the pivotal factors of cognitive development. Mental chronometry and cognitive ability. Researchers have reported medium-sized correlations between reaction time and measures of intelligence. There is thus a tendency for individuals with higher IQ to be faster on reaction time tests. Research into this link between mental speed and general intelligence was repopularized by Arthur Jensen, and the choice reaction apparatus associated with his name became a common standard tool in reaction time IQ research. The strength of the RT-IQ association is a subject of research. Several studies have reported association between simple reaction time and intelligence of around, with a tendency for larger associations between choice reaction time and intelligence. Much of the theoretical interest in reaction time was driven by Hick's law, relating the slope of reaction time increases to the complexity of decision required. This promised to link intelligence directly to the resolution of information even in very basic information tasks. There is some support for a link between the slope of the reaction time curve and intelligence, as long as reaction time is tightly controlled. The reaction times of low G individuals are more spread out than those of high G individuals. The cause of the relationship is unclear. It may reflect more efficient information processing, better attentional control, or the integrity of neuronal processes. Other factors. Research has shown that reaction times may be improved by chewing gum. The results showed that chewing gum was associated with greater alertness and a more positive mood. Reaction times were quicker in the gum condition, and this effect became bigger as the task became more difficult. Application of mental chronometry in biological psychology, cognitive neuroscience. With the advent of the functional neuroimaging techniques of PET and fMRI, psychologists started to modify their mental chronometry paradigms for functional imaging. Although psychologists have been using electroencephalographic measurements for decades, the images obtained with PET have attracted great interest from other branches of neuroscience, popularizing mental chronometry among a wider range of scientists in recent years. The way that mental chronometry is utilized is by performing tasks based on reaction time, which measures through neuroimaging the parts of the brain which are involved in the cognitive processes. With the invention of functional magnetic resonance imaging, techniques were used to measure activity through electrical event-related potentials in a study when subjects were asked to identify if a digit that was presented was above or below 5. According to Sternberg's additive theory, each of the stages involved in performing this task includes encoding, comparing against the stored representation for 5, selecting a response, and then checking for error in the response. The fMRI image presents the specific locations where these stages are occurring in the brain while performing this simple mental chronometry task. In the 1980s, neuroimaging experiments allowed researchers to detect the activity in localized brain areas by injecting radionuclides and using positron emission tomography to detect them. Also, fMRI was used, which have detected the precise brain areas that are active during mental chronometry tasks. Many studies have shown that there is a small number of brain areas which are widely spread out which are involved in performing these cognitive tasks. Current medical reviews indicate that signaling through the dopamine pathways originating in the ventral tegmental area is strongly positively correlated with improvements in reaction time, e.g., dopaminergic pharmaceuticals like amphetamine have been shown to expedite responses during interval timing, while dopamine antagonists produce the opposite effect.